Welcome to the Explainer. So today we are doing something pretty wild. We're going to build a mathematical dictionary. Imagine just for a second having the power to translate squishy, continuous, entirely geometric shapes directly into rigid computable algebra. I mean, that is the beautifully profound goal of algebraic topology, and we're going to unpack exactly how mathematicians actually pull this off. We're going to see how geometric shapes can literally be distilled down into numbers and equations that we can confidently calculate.
Now, to really understand this dictionary, we have to start by asking a kind of weird question. How do you mathematically measure a hole? I know, it sounds like a child's riddle, but this is the absolute ultimate problem algebraic topology tries to solve. And look, this isn't just pure abstract math. Whether we're analyzing incredibly complex, high-dimensional data sets in machine learning, or mapping out collision-free paths for robotics, or even trying to understand the actual fabric of space-time in physics, we need a rigorous mathematical way to prove that a sphere and a donut are fundamentally different objects. Like, we can clearly see it, but how do we definitively prove it?
Okay, let's dive into our roadmap for this explainer. We'll start with the geometry of holes, move into loops and fundamental groups, uncover the magic of covering spaces, search for the universal cover, and finally arrive at homology, the abelian upgrade.
Section 1. The geometry of holes.
So tracing this back to its historical roots, the brilliant mathematician Henri Poincaré laid the groundwork for measuring shapes way back in 1895. He realized that global qualitative geometry is, at its absolute core, completely algebraic in nature. Consider this quote from our sources. The basic idea of homology is that we start with a geometric object. Then the linear algebra and boundary relations determined by these data are used to produce homology groups. Basically, the overarching goal here is using what mathematicians call functors. Now, I know that sounds a bit intimidating, but just think of functors as incredibly reliable translation machines. You feed a squishy geometry problem in on one side, and boom, the functor outputs a crisp algebra problem on the other side.
Section 2. Loops and fundamental groups. To measure a hole, Poincaré's first intuitive solution was basically to drop a closed path, or a loop, onto a shape. Every fundamental group starts by locking down a very specific starting position, a base point. Think of it as throwing an anchor down. The loop extends from this base point, explores the space around it, and then comes right back to anchor itself again. If the space happens to have a hole in it, well, a loop might get caught around it, essentially capturing its geometry like a lasso. But here's the thing, we really don't care about the exact, rigid, microscopic path of that loop. What we actually care about is its equivalence class under something called homotopy. Now, without getting bogged down in heavy jargon, homotopy simply means wiggling one loop into another continuously, without breaking it or lifting it off the space. Imagine a rubber band stretching and moving across the surface. If you can smoothly deform one path into another, they belong to the exact same equivalence class. They are telling us the exact same structural information about the shape.
And this leads us directly to the fundamental group, denoted as pi1. It's the group of equivalence classes, under homotopy, of the loops contained in a space. And honestly, here is where the absolute magic happens. If you travel along one loop and then travel along another, you are essentially doing algebra. Just let that sink in for a second. You are concatenating paths. You are literally doing addition and multiplication. But instead of using numbers, you're using the structural shapes of the space itself. However, there is a bit of a complication in our story here. This tool, while incredibly precise, can be agonizingly hard to calculate. Because it's so heavily dependent on that starting base point, traveling path A and then path B is not necessarily the same as traveling path B and then path A. This makes the fundamental group what we call non-abelian. The order of your operations totally matters, because your physical starting position literally shifts the perspective. So it's a highly precise tool, but unfortunately, a really unwieldy one to actually compute.
Section 3. The magic of covering spaces.
All right, so to handle that unwieldy, non-abelian fundamental group, algebraic topologists use what are called covering spaces. Think of these as geometric decoder rings that help us unspool all that complex algebra of loops. Formally, a covering space is a map from a space x tilde down to x, where every point has an evenly covered disjoint neighborhood. Now sure, you could technically invent a dumb covering space made of just a bunch of disjoint floating circles mapping down to one single circle. But to get the good stuff, the mathematical insight we really crave, we care deeply about the path-connected covering spaces.
Let's look at the classic analogy for this. Imagine a standard circle as your base space down below. Now imagine the real number line wrapped up like an infinite spring or a helix, hovering right above it and projecting down onto that circle. Looping around the circle once down below perfectly translates to walking up exactly one integer on the helix above. See what we're doing? We are unwrapping those confusing overlapping loops into distinct, trackable paths. We are translating a squiggly looped path into a straight, measurable line of integers.
And this brilliantly illustrates one of the absolutely most beautiful connections in all of topology, a Gala-like correspondence. There is a perfect translation between the topological covering spaces and the algebraic subgroups of the fundamental group. Seriously, if space A covers space B, space A's fundamental group is a literal subgroup of space B's fundamental group. We have continuous squishy geometry perfectly and predictably mirroring rigid algebra.
Section 4. The universal cover. Now, this hierarchy of subgroups raises a pretty fascinating question. Is there one ultimate covering space at the very top? Like one space to rule them all? Well, the answer is yes. To find it, we look for a covering space that is simply connected. All this means is we ensure its fundamental group is entirely trivial. It has absolutely no holes. Its pi1 is just the trivial group. Because the trivial group is technically a subgroup of every single group, this space acts as a covering space for all other covering spaces. A mathematician might spend 20 minutes drawing a crazy, complicated, infinite fractal tree just to visually represent the universal cover for a wedge of two circles, but its underlying purpose is beautifully simple. It is the absolute geometric ceiling of our algebraic dictionary.
Section 5. Homology, the abelian upgrade.
We've seen how precise but kind of messy the fundamental group can be, right? So now, let's look at the optimization phase, which was formalized by the axioms of mathematicians Eilenberg and Steenrod. Let's really contrast our two major tools here. The fundamental group is based on precise loops and is rigidly anchored to base points. And because it's non-abelian, it's notoriously hard to compute. Homology, on the other hand, is based on linear algebra and simplices, which are essentially just the basic building blocks of spaces. Crucially, it completely ignores base points. By zooming out and dropping that anchor, it becomes abelian. It allows us to compute the uncomputable by sacrificing a tiny bit of precision for a massive amount of calculability.
So the absolutely crucial point is summarized perfectly by this idea. The first homology group, H1 of x, is just the abelianization of the fundamental group, pi1 of x. These aren't just isolated competing ideas. They are a unified theory. If we just change our algebraic perspective, allowing path A minus path B to simply equal path B minus path A, we unlock a far more powerful, computable way to understand these shapes. We literally just allow ourselves to act in an abelian setting, upgrading our dictionary so that the math is actually solvable.
Which leaves us with this final thought. If translating squishy shapes into rigid algebra decodes the profound geometry of these spaces, enabling massive breakthroughs in everything from robotics to high-dimensional data analysis, what other hidden structures in the universe are waiting for their own mathematical dictionary? Something to chew on. Thank you so much for joining me, Focus Learners. Keep looking for the algebra hidden in the geometry around you, and I will see you in the next explainer.